So today I want to talk to you about using icequakes to look at glacier processes. However, given the kind of topics covered in some of the other talks this week and Gonzalo's talk after this, I'm actually going to cut out the crevassing bit of this talk, and I'm just going to talk to you today about glacier sliding and how we can use icequakes to look at that. And the results I'll show you today are quite new. They're quite preliminary results, but I think they're quite exciting. So I thought why not show you them? So you guys are the first people who've seen these results. That's my excuse if anything. It doesn't make sense anyway. So first of all, what causes icequakes? So I imagine many of you might not have come across icequakes before. And icequakes are simply caused by a sufficient strain build-up in the ice, causing the ice to fail. And when this ice fails, it can cause cracks, crevasses, say at the surface of a glacier. It can also cause iceberg carving, like the carving off this ice front. This is an outlet glacier on the Antarctic Peninsula, and icequakes can also be caused by ice sliding over the bed. So as this ice slides down into the oceans, it can cause icequakes. So I'll just put on my pointer here. So you can have, and those sliding icequakes. They're what we're interested in today. So here's a picture this is a subglacial conduit in Svalbard in the winter, fortunately, because there's no water coming through. And I think it's a nice way of illustrating what I imagine is going on at the bed of both glaciers in Svalbard, but probably also a lot of Antarctic ice streams and other glacier bodies. So what we have ice, and it will slide over either till or bedrock. I think in a lot of locations now, I prefer to think of icequakes being generated over a till layer. But the ice may and the till may well have clasts either frozen into the ice or embedded in the till. These clasts might be pebbles of various sizes. So I like to think of this as kind of, we have an ice till interface, but we also have a lot of complexity in terms of what's going on with these kind of clasts and stuff. And I won't talk about that too much today, but it's something to bear in mind what this interface might look like. And as the ice slides over the till, we generate this seismic energy, which is released, and we detect it at the surface using seismometers. So why are basal icequakes important? Why do we care about them? Well, ice flows into the ocean and hence causes sea level rise, primarily in two ways. The first is through deformation, so the ice flowing off the continents into the oceans viscously. I guess a bit like if you poured custard over your dessert and how it would flow over the dessert if you've got thick custard. But ice can also slide into the oceans. And we think this sliding is much greater than deformation for a number of ice streams, certainly in the Antarctic, which is where I focus my research at the moment. And here's the Antarctic continent. And this is from Reno et al. 2011. And this just shows the velocity magnitude. And the pink regions, I guess the bluey pink regions, are regions where the ice is moving upwards of 500 meters per year. So very, very fast flowing ice. And we think that a lot of this fast flowing ice, other than that, obviously on the ice shelves, is flowing via sliding rather than deformation. So sliding is a really important process for governing how quickly that ice on the Antarctic continent and Greenland can float into the ocean. However, and this is a statement I really like from a paper, well, I guess a decade ago now, basal drag is a fundamental control on ice stream dynamics, as we just stated, but it remains really poorly understood and constrained by observations. So typically what many modelers do, and people looking at ice movement at the moment do, is they'll take surface observations, say from GPS or remote sensing observations like satellite observations, and they will take that surface velocity, and then they'll assume a deformation signal, or they'll assume a model of deformation in the ice, or how much the ice is deforming, and then back out a rough approximation for sliding that way. What I'm going to show you is a way of using icequakes to get to this sliding directly. So we're going to remotely sense the sliding using these icequakes. Which I think is exciting because these are probably some of the first observations ever remotely sensed, certainly on a large sort of scale of an ice stream of sliding at the bed. And so what we're going to try and do is look at this basal drag. And I think, speaking to modelers, the two parameters that I think are useful, I mean, Gonzalo will maybe correct me in his talk next, but two parameters that are really important for modelers in understanding, in creating an Einstein model and modeling this boundary condition are firstly the basal shear stress, or the drag over a certain area of the bed, and the slip, or alternatively, you could think of it as the sliding speed if you look at slip over time. And the sliding speed is exciting because, well, important because it governs how fast this ice ends up in the oceans if we're dominated by a sliding regime. And so I'm going to show you these observations that hopefully will help to constrain this. We're getting these observations from these ice quakes that I've talked about. So the data we're going to use to look at this are some ice quakes from Rutherford Ice Stream in Antarctica, collected in 2019 by some colleagues in the British Antarctic Survey. And here's a paper that came out earlier this year looking at this data. And there's about 200,000 ice quakes shown by these blue scatter points on this right-hand figure. And you can't necessarily see it that clearly, but you can take my word for it at the very least that they're located in distinct clusters. So you can see there's little clusters all over the bed. Yeah, determined to some extent by our network geometry as to where we detect them. But you can see there's lots and lots of clusters. There are about 950 clusters we observe. And I'm going to show you results from each of those clusters. And hopefully I'm going to show you how we can derive shear stress and slip rate for each of those clusters at Rutherford Ice Stream. And Rutherford Ice Stream is moving, I should say, at about 350, 360 meters per year, something like that. So what we can do is we can get certain data from ice quakes. So a bit like an earthquake, you can get out the moment magnitude, i.e. the size of the ice quake or earthquake. You can get out something called the corner frequency, which I won't talk about anymore, but feel free to ask me about it later if you wish. The inter-event times, so the time between these ice quakes. Things like the fault area, so we can calculate how big the fault is, where the slip is occurring. And also things like the stress drop. So that's how much stress is released emitting seismic energy, but obviously there's also stress released due to frictional flow, which I'll talk about in a second. So what we do is we take those ice quake observations and that we can kind of quantify the parameters for, and we also take this rate and state friction model, which is commonly used in engineering problems, but also a lot in earthquake physics to describe earthquake rupture. And it's based on what we call a spring block slider model. So we've got a block here and a spring, and if we pull that string with a force or a stress, if we think about it in terms of force over area, then if that block's got a certain normal force exerted on it, then we'll have a friction at this interface here, and that friction governs the fault properties. And this model can be used for earthquakes, but it can also be used, well, I'm also assuming I can use it for ice quakes at the bed of a glacier. And I know it's not a standard sliding law for a glacier, but it gives us some way of grappling at these parameters, this shear stress and the sliding. It's governed by this equation here, if we assume that the state variable is time invariant over ice quake duration. And basically, this governs the kind of static velocity independent friction. And then this describes the either velocity strengthening or velocity weakening friction, this term here. A and B we take as constants. This is the normal effective pressure, so that vertical pressure on the block. And this is the velocity at a given point in time. And what we can do with this model is, if we have a sufficiently low effective stress exerted on that block, then the block slider system is said to be stable. And then as we increase that effective normal stress, what we can do is we can start to move into an unstable regime. And in this unstable regime, we call this a velocity weakening regime. And this is where we can nucleate ice quakes or earthquakes. And so this region here, where we have a sufficiently high velocity and a sufficiently high normal stress, means we can generate these ice quakes. And we'll use that information to calculate the slip in the system. And so what we can do from this is hopefully get out an idea of the total shear stress, tau, and the velocity of the ice, which in this case is V0. And that velocity is out the bed, I should say. So our first result is we can look at getting out effective normal stress. We need the effective normal stress to calculate everything else. And what we can do is we can get that from this equation, which I won't talk about, but we can basically use the stress drop to calculate the effective stress from that rate and state friction law. And what we do is we end up with these results. So this is normal stress here versus time, and I'm going to show you all the plots I'm going to show you on this for the results of this data on the same time axis over about 7 or 8 days in 2019. And each of these lines represents a cluster. So we can see we've got various clusters active at various times. And these clusters shut on and off depending on whether the system is stable or unstable. And we can see that we can measure the normal stress, effective normal stress on the fault. And we think this effective normal stress is governed partly by the weight of the ice acting on the bed, but also some water presence and a certain water pressure present in that porous till that presumably can modulate this effective normal stress. And I guess that's crucial to all results. We see modulated effective normal stresses over time. And this red dashed line here is the maximum effective stress we would have if we just have ice. So if we have no water present, so no water to lift up the ice, only the weight of the ice on the bed. And we can see that all our clusters don't go above that maximum effective stress, which is a good sanity check. It's a good verification that our data is perhaps making some physical sense, in the sense that we can't, we don't predict that we see effective stresses greater than the effective stresses that we could possibly generate in this system. But we do see effective stresses very close to this, suggesting that in some places on the bed at certain times, there is no water present. The second thing we can get out, and this is the, I guess, key result 1 of 2, is that we can get out the total basal stress, or the total resisted stress to flow, the drag per unit area. And that's shown here in this block slider system. And again, we get these clusters. They have different drags, and this is a log scale. So we can see there's quite a significant difference of, say, 2 orders of magnitude, 3 orders of magnitude in the basal drag over time. And what we see also is that this is modulated on the order of hours. So we can see that if this system is modulated by something like water, that our basal drag, our basal shear stress is modulated by orders of magnitude on the order of hours, which is an interesting result and sort of brings into question whether something like tides could be modulating this, or pulses of water flowing through a hydrological system. And again, for sanity check, to provide a sanity check, I've plotted on here, these dashed lines here are the maximum driving stress. So the maximum stress you could count, you counter this drag stress with, depending on the gradient of the bed. The bottom dashed line is for a 5-degree bed incline or decline, and the top is for 20 degrees, which is quite a significant bed incline. And we can see that most of our icequake clusters are well below this 5-degree line, but certain ones go above the 20-degree. But that is possible and potentially feasible at Rutford, because the fault area, well, the radius of the fault is of the order of 10 to 40 meters. So these areas are sufficiently small that we can probably have that kind of variation in topography at the bed. But there is a fair bit of uncertainty on these results. So that's the basal shear stress, which is obviously is useful for modelers, putting it in as a boundary conditions that ice dynamics models. To get out the slip, we also have to get out the bed shear modulus. And I'm just going to show you the bed shear modulus results here, because I think they're another good sanity check to check that our rate and state friction law is potentially physically reasonable. What I've got on here is I've got the basal shear modulus plotted against time again. And what we do is we can see that this dashed line here is the shear modulus of till measured seismically for an ice stream called ice stream B, or Williams ice stream, one of the Cyprus coast ice streams. And that's just the till measurement for the shear modulus in situ at the bottom of a glacier. This top line here is the shear modulus of ice. So throughout this talk so far, I've assumed that the source is either at the ice bed interface or in the till. But if the shear modulus, if the source is in the ice, then we might expect to see a shear modulus of the ice, and this theory might fall apart. Unfortunately, we don't see any ice quakes with shear moduli of the order of the shear modulus of the ice. So we're fairly confident that ice quakes are at the interface or in the bed. The fact that we have ice quakes lower than this bottom line is not a worry. That's just one measurement at an ice stream. And in fact, it's actually very difficult to get this measurement out. These are some of the few measurements we do have of an in situ shear modulus of a till in an ice stream. So we can see in some cases, these shear moduli go very low, 2 orders of magnitude lower than the shear modulus of the ice. So the final result I'm going to show you is just the slip rate. So the velocity of the ice at the bed and the sliding velocity, which I think is probably arguably the most important parameter I'm going to show you today, because this really governs how fast that ice is ending up in the oceans, and therefore how quickly sea level rise could be occurring for our observed ice stream. And what I've got plotted on here is slip rate, again, versus time. And this dashed line here is the Rutherford mean surface velocity, which is about 1.1 meters per day. And we can see that actually our icequake results, most of the clusters very much agree with this sliding, certainly within sort of, a 50% agreement, which is good for seismic observations such as these. But you can see that the sliding does change over time. So we have quite a variation, again, presumably modulated by this normal effective stress, and therefore the strength of the till and the pressure on the fault interface. But we can see that these results do generally agree with this observed surface slip rate, suggesting that the models of Rutherford ice stream are probably correct, that pretty much all the slip is accommodated by sliding. Sorry, all the motion of the ice, surface motion of the ice, is accommodated by sliding rather than deformation. So yes, thank you for listening. So to conclude, we looked at this statement: basal drag is a fundamental control in ice stream dynamics, but it remains poorly understood or constrained by observations. Hopefully, these icequake observations maybe shed some new light on that process and provide some observational constraints, which hopefully can in the future be used as boundary conditions for these numerical models, which is so important for computing sea level rise projections. And we can use these icequakes with this rate and state friction model, which is obviously is an assumption, and let's take it as assumed for today that it's correct, but it might not be the correct model to use. What we can do with that is then we can back out basal shear stress at the bed, sliding velocity, and we get for free, we get out the effective normal stress and the shear modulus of the bed as well. And we've done this for 200,000 icequakes in 950 clusters over a sort of 10 kilometer square, well, 10 kilometer by 10 kilometer region of the Rutherford ice stream. So we can then now take these results and plot them up spatially and look at the spatial variation of slip and shear stress of the bed. Yeah, so thank you for listening, and feel free to ask any questions.
Wonderful, thanks very much, Tom. That was fascinating. And if anyone has any questions, please do raise your hand or drop a note in the chat, or just unmute yourself and go for it.
I'm gonna go ahead because I have to leave in a couple of minutes, so I might not even be able to stick around for the whole answer. But I wanted to say this is really interesting, Tom. But I'm very confused about. I mean, the observations that you actually make are seismic observations. So you're starting with seismograms, right? And you haven't really talked at all about seismograms in your talk. And I think I'm really unclear on how you go from the seismograms to all of the relevant parameters. And in the rate and state friction model, which seems reasonable to apply, you've got mu naught, A, B, and V naught, all of which are parameters. And the answers that you get will depend on those parameters. And I didn't see how you calibrated your model at all. And in these comparisons, the velocity that you've obtained, however you've done it, seems to be at or below the sort of long-term average sliding velocity. But how would you get a long-term average sliding velocity if the fastest motions are at or below the level of the mean sliding velocity? Is there no background sliding at all? So
Yeah. So yeah, sorry, this is the first time I've presented this work, and I wanted to make it for a broad audience, so I didn't talk about any of the kind of how we get from the seismic observations to the kind of data out. And it's a really valid question, and I think we should probably have a proper discussion about this, Rich, because I think I can answer all your questions, but obviously it take a bit of time because they're great questions, but very detailed questions.
I trust that you can, and I would love to make an appointment to discuss it, because it, as I said, I think it's really fascinating results.
Yeah, definitely. Let's do that. Let's catch up at some point, because I'd also like to sanity check the assumptions I've made, because obviously you have to make a lot of assumptions here. I guess what I will say for the audience is that there are a lot of assumptions that go in, and we take, for example, mu naught A and B, we take from literature. They turn out to not vary as much. The literature measurements of them don't vary as much as these seismic observations do. So I think they have less impact than the error induced from the seismic observations. Yeah, I'll leave it there for that. But I would say behind all this, there are a lot of assumptions and a lot of complexity that is really difficult to describe in a talk like this. So yeah, I'll leave it there rather than try and answer all that in one go. But yeah, sorry, Rich.
We'll be in touch by email. Thanks. And I haven't met Gonzalo. I'm really sorry that I have to miss the next talk, but thanks for organizing.
Super. Well, I'm glad that this kind of connection can be facilitated through these meetings, so it's already kind of a good result. Tom, I've got a question which is about the nature of the array and the measurements themselves. And sorry if I missed this, but I didn't really catch how that looks and how it was installed. Is it on the ice? Is it next, on the bedrock, or how does it look?
Yeah, great question. So here's the array. This is the seismic network. You can see it's quite small there. This is with the ice stream sort of bounded by here, and then this side. So it's about 30 kilometers, 40 kilometers across. And the array is comprised of, I think, about 30 instruments in a grid, and they're all deployed on the surface of the ice stream. So what we do is we dig a hole and bury the instrument, and they're all geophones. So they're all, I don't know, sort of as big as, how big are they? Like, I don't know, 20 centimeters by 20 centimeters by 20 centimeters sort of size. And we bury those in the ice, and they detect velocity motions at the surface. Yeah. Nice.
So they must be picking up noise from all other kinds of things going on in the glacier. I guess crevassing as well, which is something you deliberately didn't talk about in this talk. But surely that the information they carry the measurements that they make can tell you about quite a lot of different things going on, and is one of the challenges, therefore, to sort of deconvolve those things and focus in on what you're interested in.
Yeah, definitely. So yeah, there are a lot of other sources. Generally, a rule of thumb for seismology is you generally want your sources to be, your earthquakes or whatever, to be within your array or your network. That's not always true, but for the sake of like analyzing, say, crevassing or whatever, or another source, you really want to kind of have your network over that point, that location. For example, crevassing, you have a lot of crevassing at the kind of shear margins of the ice stream. It's a bit difficult to deploy seismometers there, so we haven't done that. But yeah, that's just one example, I guess, of how you might focus and look at other sort of aspects of the data set.
Nice, thanks.
Yes,
okay, anyone else for a question?
So thanks, Tom, for the talk. I was just quite curious about the fact that you obtain these measurements from icequakes. To what extent are icequakes a sort of, how can I say it? So to what extent can we expect icequakes to occur in any sort of setting, so that you can generalize the results of your measurements to sort of different ice sheets or geographical settings?
So, sorry, so just to rephrase your question maybe if I can, just so I understand how to answer it. It's a good question, I think. Are you asking, basically you're asking, like, this is a very specific observation, what's the applicability of this elsewhere? Because are these ice quakes just occurring at, say, Rutford ice stream, or, you know, what happens if you don't have ice quakes? Can you make this observation? I guess you can't make the observation if you don't have ice quakes. You need the ice quakes to be there, obviously. There are ice quakes at a number of ice streams and glaciers on a number of scales. So we see ice quakes in Greenland at outlet glaciers. We see ice quakes in various ice streams in Antarctica. We see ice quakes in glaciers in the Alps, for example. So these sources are available in a lot of places. The other critical thing, and I think the other, to try and answer your question, is we assume here that the ice quakes, for the given period of time where the ice quakes are active, that all the slip is described by releases of seismic energy. So we have a switch on of seismic energy, and then all the sliding is accommodated by seismically, and then we have a switch off, or seismically and by friction that's accommodated for in the seismic energy, and then they switch off again. And so we can only observe during that period. We can't make these observations outside of that period, and I guess that's a really limiting factor of this approach. My hope would be that we can see ice quakes at enough places that we can characterize the properties of the till when the ice quakes are active, and then back out at least an upper estimate of what the shear modulus of the till is when the ice quakes aren't there, if that makes sense. Yeah, great question.
And would you expect ice quakes to also occur over hard beds, where it might not, well, till deformation might not be like the predominating mechanism?
Yeah, certainly. We think we observe ice quakes on bedrock, ice-bedrock interaction in glaciers in say the Alps. I think in the majority of ice streams, most of the bed is probably, well, maybe it's till, but I don't know actually. I mean, I guess your talk is talking about bedrock on ice, so I don't know. I'll leave that open, but we can observe ice quakes on bedrock, I think. But it's quite a big question that's still potentially unanswered.